Okay, let's look at a few of the characteristics of mutualism. Mutualisms are categorized by the type of benefits that result. Trophic mutualisms, trophic, food. The mutualist receives energy or nutrients from its partner. Example of this includes the leafcutter ants and the fungus, mycorrhizae, and coral alga symbionts, the coral and zooxanthellae. Habitat mutualisms, one partner provides the other with shelter, living space, or favorable habitat. An example of that is this pretty famous example, the pistol shrimp, where the shrimp can dig a burrow. The goby lives in the burrow with the pistol shrimp, but the pistol shrimp can't really see, and so when they leave the burrow, they kind of effectively hold hands, but the pistol shrimp puts an antennae on the goby and helps them kind of go out and forage when they're in the burrow that the pistol shrimp created. The pistol shrimp guards it and helps keep the goby safe. And so it's this interesting habitat mutualism between two extremely dissimilar species, but it seems to work pretty well. And one species may have or may provide favorable habitat by altering the conditions or increasing the partner's tolerance of the condition. And this is an interesting example of a grass that grows next to a hot spring. It has a fungal symbiont, an endophyte, endo inside phyte plant, or that helps it tolerate high temperatures. And so they looked at this fungal symbiont in this grass, and if you remove the fungal symbiont, grow the grass in these warm soil temperatures near these hot springs, without the fungal symbiont, they all die. With the fungal symbiont, a great number of them survive. And so by having this internal symbiont, this fungus that allows the plant to occupy habitat it couldn't prior, with nearly 100% mortality if it's not there. So it's really pretty interesting that it can really make that much of a difference, that a fungal symbiont can really change the tolerance for something pretty foundational, like being able to withstand a high internal temperature. Although both partners benefit in mutualism, there's also costs. In the coral algal mutualism, the cost of the coral includes supplying nutrients and space. The cost of the algae is, sharing some of the delicious carbohydrates it just fixed via photosynthesis. In mutualism, net benefits must exceed net costs for both partners. Meaning that, again, like there's no free lunch, that to engage in these partnerships, it costs resources. Presumably the benefit of that partnership outweighs the cost of those resources. And it can be dynamic depending on the current suite of environmental conditions. And so you can have the interaction of two species. This is a pretty interesting one. Looking at ants, excuse me here. Looking at ants in a tree hopper. And I'll show you an image of a tree hopper and another image of a tree hopper here again. But there's these small bugs that live on trees in South America, and they secrete honeydew, a sugar solution that the ants feed on. And in turn, the ants help protect the tree hoppers from predators. So here's the tree hoppers here. They're kind of hard to tell. I mean, there's these kind of white things. They're pretty compressed, almost like an amphipod. And they kind of have this high ridge. And so the ants form a facultative mutualisms with insects that secrete honeydew. It's a sugar substance on which the ants feed, and the ants will protect the tree hoppers from predators and parasites in exchange for the honeydew. So the the tree hopper is actually producing a sucrose solution that the ant's directly feeding on. And they do this in exchange for protection for the tree hoppers, but depending on the suite of predators and parasites on the tree hopper out there, there might not be any predators or parasites around, and so therefore the ant's not really doing anything, but they're still getting some benefit out of it. Or there could be a fair number of predators and parasites that would normally consume the tree hopper, but the brave ants are fending them off, in which case there's a great amount of benefit. Or there could be really, really no change. And so we could think of this interaction as mutualism. Ants are benefiting, they're getting honeydew. The ants are chasing away, defending the tree hopper, so they're getting a benefit. You could think of it almost as parasitism, where the honeydew really are the tree hoppers really are not getting any benefit at all from the ants, but the ants are retrieving benefit from the tree hoppers. They're getting the sucrose solution, but if there just happens to be no predators or parasites for the tree hoppers, then having a bunch of ants around to protect them, it isn't helpful, and you're still feeding them. So it's a massive cost. Or it could be a commensal situation where there's enough predation and parasitism around to justify, on a life history scale or evolutionary scale, justifying helping to feed the ants, but it's not really a plus or a minus for the tree hoppers. I mean, there's some cost there to producing the honeydew solution for the ants, and that's relatively the same amount of cost it would be to defend themselves, the tree hoppers defend themselves against the predators and parasites, and so it's kind of a wash. So you could have the same really group of organisms, tree hoppers and ants living on a tree, and depending on the season or the year, that relationship could be defined as mutualism, commensalism, or parasitism, depending on what else is going on, depending on basically the number of predators and parasites that are going for tree hoppers. Here's another image. That's the tree hopper there. They're kind of cute little bugs. Here's the ant bravely protecting the tree hopper eggs as the tree hopper lays its eggs. The ant is here protecting its tree hopper in exchange for that sweet, sweet honeydew. The mutualists may withdraw rewards. In high energy environments, plants can easily get nutrients, and they may reduce the carbohydrate reward to mycorrhizal fungi. So mycorrhizal fungi really extend the surface area of the root system, and they're able to bring in more water nutrients. Well, perhaps under good conditions, you don't need that extra help, so why pay for it? So they can withdraw some of their rewards, in this case carbohydrates, to those mycorrhizal fungi. If providing them, if there's cost benefit analysis changes and they really, there's not an additional benefit to having those mycorrhizal fungi. Additionally, cheaters are an issue. Individuals that increase offspring production by overexploiting their mutualistic partner. If this happens, the interaction probably will not persist, but there's always a certain percentage in nature, and there are several factors that contribute to the persistence of these mutualisms. And this is an interesting one of an obligate mutualism between a yucca and a yucca moth. And so yuccas, cactus-like plant, is in the southwest. It's only fertilized by a yucca moth. The yucca moth collects pollen from one yucca and lays the eggs in another, depositing the pollen in the flower, and it lays a number of eggs in this flower as well. These eggs will, as they develop, eat seeds in that flower. And so the yuccas agreed to this they form this obligate mutualism where the moth has a safe place to put their eggs. There's food for them in the seeds, and then the yucca gets fertilized. And the idea is that the larvae will eat some of the seeds, but not all of them. And what I thought was interesting is that the yucca can detect, supposedly it's like hard because it's not a sentient being, but there seems to be a high correlation between individuals that lay a whole bunch of eggs in the flower, and that flower then being cut off and aborted. Meaning that if you were to game the system as a moth, you would, instead of laying a few eggs, you would lay a whole bunch of eggs in that flower and hope that they would all survive. But the yucca seems to drop those flowers at a higher rate. And so here's the mean retention, which the yucca typically retains about 63% if it's well, that's not 63. The book said 63, huh? Well, I swear it said 63. I just read it. Anyway, it doesn't matter, I guess. Yeah, that's funny. Yucca retains 62% of the flowers. Okay, well, anyway. So this is the percentage of flowers retained to maturity combined with the number of moth eggs present. So if you lay 6 eggs and below, the likelihood of that flower being retained to maturity is quite high. If there are more than 7 or more moth eggs, that likelihood of being raised of the flower coming to maturity is quite low. And this is interesting because the moth will come along, lay its eggs, and if normal is like 5 and they put 10, like sweet, I game the system, they fly off, and it's not immediate, but that flower is dropped or aborted before the seeds become mature, and so all of the eggs within that flower then perish. And so it's sort of like that lag between giving an exam and hearing back from all of the websites that post answers and then being able to go back and void those exams, right? Like there's some lag where you can cheat and you feel like it worked, but there's a lag that's like a week or 2 later, and then you wind up getting a 0 on your exam. So it's similar to that. So don't lay too many eggs in a flower. And it's like important. It's like easy to do. Say, oh, they're doing this to help out. Blah blah blah. It's like, no. Everybody's in this for themselves. There is no altruism in nature. Everybody's working on behalf of their self-interest, and there's sometimes when the self-interests align, and 2 species can both derive benefit from the same interaction. In general, mutualism evolves and is maintained because it has a net positive effect for both partners. Okay, that's just a quick one, then we'll go to the ecological structure around mutualism, and that should be it for chapter 15.